be here in front to introduce our facilities in Egypt. Thanks to Haich to giving me this chance to be here, and thanks to Rose also for giving me the chance. Actually, maybe some people, David knows, visited us last year or 2 days before, and he knows about our facilities in Egypt. But other people might not knows about our facilities. So I'll start in giving you an information that the astronomy in Egypt started early in 1839 in what was called the Bulak Observatory. Then it moved to the Abbasiya Observatory in 1872. Then, because of the pollution, of the light pollution of the city, it moved to the Hilwan Observatory in 1907, which is now the headquarters of our offices in Hilwan. But also because of the light pollution, we moved to the other observatory, what's called the Kottamia Astronomical Observatory, which contains the our 1.9 telescopes, which is the brother or the sister to your telescope here in Sutherland. So this telescope, as you know, is the only one in Middle East and second in Africa after yours. What started working in 1964, and we had an upgrade for this. The optical system for this telescope was upgraded in 2003 because of some problems related to the surface of the mirror that resulted from the coating plant that had some problem in the oil, diffusion oil, which got into the surface. We were unable to repair, and so we got another optical system. We had now another mirror, another secondary mirror, Cassegrain mirror, for that purpose. So this is our telescope, and which is similar to yours, to your telescope in Sutherland, which you have the parameters of our telescope, but unfortunately the Cody focus is not now working. We have only two focus, Newtonian and the Cassegrain focus. So this is the optical system upgrade, which we had in 2003, and we have also an upgrade for the CCD camera. This is the first CCD camera we used in 1997, and we also have an upgrade for the aluminizing plant, and we had some spectrograph from Kottamia as a gift to us, but it didn't work any time, actually. And we had the most important telescope control system refurbishment in 2007 and 2008. And then we had the Kottamia CCD camera system, another CCD camera. And so also the final one was the Kottamia Fent imaging Spectro-Polarimeter in 2019. So this is I'm sorry, the optical system upgrade. This is our old mirror now is have in the entrance of the dome, and this is a new one while we are making the coating. This new mirror was made by Jena in Germany. Zeiss in Germany, and it has made of Zerador glass ceramic, and has these parameters for the new mirror, and now it's working well. Also, we had some problems also with the company after some fixation points. These points, some fixation points was released, and we have some problems with them, and we finally fixed it, and now it is working very well from that time. Also, we have an upgrade for our aluminizing plant, and it is now working with the advanced SIMENS PLC. We use the pneumatic operating system from Balzers from Austria, and it's now working very well. Actually, it takes only about 5 hours to coat all the mirror, which was previously taken maybe 10 hours or so, and it was a totally manual operation. So now it is totally automatic operation, and all the operation take for 5 hours only. So that's a very good operation we did in our observatory. This is the first CCD camera we have. Also, it was 1K by 1K, and it worked for some time. It has an auto guider also, but after some time, it was not working, and we had to go to another camera because this one was not working very well. This new camera was purchased after the refurbishment of the Kottamia telescope control system, which is the major upgrade we had in our telescope or in our observatory, and it replaces the obsolete 50 years components with the up to date ones that are working now with computer control, totally working with computer control, and it improved the pointing accuracy and the tracking accuracy with the without or with the auto guider. It's now working very well and have communications observing a telescope, and the dome now can follow the telescope movement, which was previously has to be pushed manually controlled with one man, which is responsible for that rotation. So I will show you only some photos of the old system and the new system in order to compare. This is the control desk that we previously have, but might be you have now or you have before, and this is the control panel, which was a hassle actually, because if any wire has disconnection or so, it was a big problem to discover which wire is responsible for the non-operation of the telescope. And this is the track motor and driver, the old one. The quick motion motors also, these ones, and the all system encoders. It was only also the very old, and it is not so precise. Newtonian focus, big problem also. Cassegrain focus, and this is the dome control that has push buttons that has to be. We upgraded it to wireless control. We made it ourselves, but it also has some problems in communication with this control box. This is all CCD cameras that I talked to you about now. This is 1K by 1K. So the problem with this old system that it was not having any limit switches for telescope to protect the telescope from any during its movement. And also that it didn't have precise timing for object location in the sky, and it had a power dips when the dome is moving. There is a power dips in the electricity because we have in our observatory we have local generators that is not connected to the network, the electricity network. So it was making dips that was affecting the computers working at that place and other instruments that was working. So, and also there were no dome follow-up of the telescope during the observation. This is our new upgraded system that had now what's called ACE dome control, ACE, this one control cabinet that has mainly two motion cards. The first card is the motion control card, and the other one is the 96 channel digital card, which reads the encoder positions and so on. Sorry. Okay. This is our new upgraded system now. You can see now the control cabinet. It is very organized, and the power cabinet also, and the control, the computer control, which is our rack mountable computers, which have also a GPS for precise timing. This is a motion control board, which is it can control the 8 axes. These are the 8 axes because we all in the beginning we have 8 axes. We have an auto guider inside the control box, and later on we discarded these 4 axes of the auto guider when we had the Kottamia faint object Spectro-Polarimeter instrument. So this is the motion control card, which now controls only 4 axes. And this is the motors, upgraded drive motors. They are very precise and have a micro stepping controller with high precision accuracy, positioning accuracy. This is the track motor also has been changed like this. This is the new one, track motor, and it can be controlling. We can control the parameters of the motor in order to have the tracking velocity or so on. And this is a digital input-output 96 board, which reads the absolute encoders and hand paddle and filter wheel encoder and other miscellaneous devices. This is absolute encoder, which have very high precision resolution that is connected to the axis of the right ascension and declination, and also on the focus. This is the resolution of our angle encoder. This is the Peter Mac, actually, which has a company that implemented with the help of our staff there. And he asked me to tell you that he is sending you his greetings for whom who knows him. So I think he visited you some 20 years ago or so. So this is absolute declination absolute encoder also, and this is the Newtonian focus encoders and the Cassegrain focus motor and encoder. This is the limit switches that was not before in our old system. This is Cassegrain focus limit switches also. We have also some hand paddles for manual control if it is wireless control, and we can also use it for manual control if we need to make this. And this is connected also to the computer, and the computer is interfacing this to the control system. This is the dome automation. Also now dome is now following the telescope, totally following the telescope while observing. It doesn't need anymore to someone to push buttons. The rotation switches. This is the smart dome, which is responsible for the following the dome to follow the automation. This is also the dome soft starter that we had and which take the problem of the power dips that we had before, and now we don't feel that there is power dip because of this dome soft starter. So the telescope has the following safety features actually, and now all axes has been protected by limit over travel switches and by intelligent software settings also. The physical emergency stops push buttons for the telescope was in the control room and the control panel, and also in the control Newtonian focus. And we have emergency stop button in the AC control software. So this is the main controls of interface for the telescope. It is very neat, and when you compare it to this one, you can find that there is a big difference between the old system and our new system now, which we can sit on the observing room and do everything while not taking any attention to the telescope or to the dome or anything else. And this is the telescope performance. I can tell you that we have now 3 speeds for the telescope, which are the tracking speed, guide speed, and city speed, and the slow speeds for the pointing. And now the pointing accuracy of the telescope is better than 12 arc seconds. When you point the telescope to any object in the sky, it is better than, and it is maybe better than this when you have a pointing model for the telescope. And the tracking accuracy is also very precise, and which you can find that it is within the plus or minus 0.075 arc seconds in 2 minutes without an auto guider. With auto guider, you can find everything is okay. So the new CCD camera system that is now called old CCD camera system, that we have now a problem with its controller and this controller, I am here for repairing this controller because we have some problems with our new camera, and we need to make this CCD camera working. And this is I am here with the help of Hitesh and Brian. I thank you, thank you to them very much for the help. And Alhamdulillah, we now repair the controller. There is still some very small problem. We hope we can solve today or tomorrow, inshallah. So this is all the camera CCD system, which is typically the same as our new camera. But our new camera I will show now is attached to the Kottamia spectrograph, and the controller is attached to the CCD itself, to the DOR itself. We cannot separate them from each other, so we have to use either two controller and CCD with each other, this one or the other one. So this is our what I call the most advanced instrument we have now, and this is called Kottamia Imaging Spectro-Polarimeter, which has 4 modes of operation. Actually, it has direct imaging, it has spectroscopic mode, it has a polarimetry mode, and it has spectropolarimetry mode. So I will give you some information about this instrument, which is attached to the Cassegrain focus of the Kottamia telescope, and it has a focal reducer to create an F12 image at the slit plane. And this optical layout, actually, we got it from the Kanata telescope in Japan, and also from the Subaru telescope in Hawaii. So the KFISP actually turns the F18 beam of our telescope into F6 beam at the science detector plane. This is the optical design of the telescope, which has 4 parts actually. This is the corrector. This is the corrector part, which has initially has 3 elements, but now we had another corrector because this one has also some problem. And we had to change it because of some problems I will show now we had in this instrument, and we spent about 3 years in order to change from this design to the other design. And this is the collimator part, which has 5 elements of lenses, and this is the photometric and spectroscopic and components, polarimetric components, and this is the camera part of the terrain of the telescope. This part is attached to the CCD camera. This part is alone attached to the CCD camera, such that we cannot separate it from the camera. So corrector design was, as I told you, has only 3 lenses. It has some problems. It has the position of axis field guider barely passes through the lens, and so the lens is too small for an off-axis guider. And the triplet doesn't leave this is the effect of the corrector. Actually, we have fall-off illumination in the center of the image, as you can see now. It is very clear at the image, and we had to find the solution for this problem. And we can see also here for this is for sky flat, and this is for the internal flat of the instrument. So now we have the quadruplet focal reducer instead of the previous one, and it is designed to work with problems still present, but it is not like before. It is better than before. And also because it now has 4 elements, is able to better compensate for the image radial fall off. And it now we can give us the opportunity to have the guide field in order to make the guider working, which was not working at the first operation. So now this you can see now the 4 quadruplet elements now, and now the rays can enter, and we can find now some space for the guider, which is now working very well. So this is the collimator design. Actually, it has 5 elements, and it is made of O'Hara eyeline glasses, very high precise glasses. This has no problem, and this is very good instrument actually. and it is giving the focusing of the instrument while we are observing. And this is a camera design also. It has 5 elements also, and it magnifies the primary focal plane by 1 to 2. This is the collimated beam section, which contains the filters and wave plates of the polarimeter and Williston Pros, and the grisms for the spectroscopic observation. And this is the operating modes of our telescope, which are 4 modes actually: photometric, polarimetric, spectroscopy, and spectropolarimetry. Unfortunately, the spectroscopic resolution is not so high. It is only ranges from about 300 to about 1,100. But it is okay. Well, we have now instruments that have 3 modes of operation. We have direct imaging that we have before. We had now polarimetry we didn't have before, and also we have spectroscopic observations that we didn't have before. So the calibration system we have in the instrument, we have an internal calibration system that we can use to either to get flat fielding or to use it during the spectroscopic operation. This can slide from direct imaging or to spectroscopy by moving this slide either to have the object from the sky or to have the internal flat fielding or the spectroscopic operation. This is the optomechanical design of the instrument. And you can see now this is the calibration system that I talked to you about now, the corrector. This is the slit guider assemblies, and this is the polarimetric components inside the cubical box, and this are the 2 drawers for the filter wheels and for the grism wheels that we can take it out and put it easily, very easily now without any problem. And this is a CT camera, our new CCD camera, which is attached to the camera lens here. So this is the calibration system corrector assembly that can move either to observe from the sky or to have the internal flat fielding or to have the spectroscopic imaging. And this is the guider and slit assembly. Also, it can move now. This is the guider camera that can move this one. It has a mirror here, 45 mirror that takes part of the field, and it can guide the telescope itself. And we had problems with this camera before when we had the triplet focal reducer, and now it can work without a problem. But the camera itself has been changed as when sorry, that's a problem. Have to be far. So this is also the slit camera assembly. This is slit camera. It's fixed in place, and it can see the slit all the time to see how long is the slit and what width of the slit. Can see the slit, and you can control it also. This is the guider assembly, and this is the collimator assembly I showed you now. Collimated beam section that contains the drawers for the filter wheel here, and for the polarimetry components, and for these grisms for the spectroscopy. And this is the last part, which is the camera portion of the telescope. You can see here now. This is the filter wheels, grism wheels, and polarimetric components. Now we have half wave plate and quarter half plate, and we have Williston prism now. This is a very expensive prism actually, and also wave plates are very expensive parts of this polarimeter. So this is the CD camera, and this is the camera lens that I talked to you now, and it is attached to the camera itself. So we have to use this camera with this camera lens. So because now we have some problems with this camera, we have some contamination inside the viewer on the surface of the chip itself. So we need to clean it, and we need to move this lens from this viewer to the other viewer that I'm now here for repairing for its controller. So I hope we can get it working, and then we can get this out and put it on the other viewer. But the problem is that the last lens of this camera lens is the viewer window itself. So we have to be very careful in order to get this lens out from the viewer, and the chip will be exposed to air, and we have to make it this in a very clean room, and we have to be very careful while doing this process. This is as I told you now, this is the last element of the camera, which is the viewer window itself. So we have to take it out from this viewer to put it in the other viewer. This is the pinhole Venetian imaging slit masks. We have 4 image masks actually. This is the what's called pinhole, and it has some holes which we can use to make the focusing of the instrument itself. And this is the Venetian blind, what's used for the polarimetry, and this is direct imaging, and this here is the slit mask. Also, we have the instrument rotator for the telescope. We can now rotate all the instrument in any direction by 90 degrees, right or left, such that we can have change the field to be in any desirable one. If you want to rotate the whole instrument, you can do that. This is also the guiding and the slit camera. And this is the new camera, the guiding camera, because the previous one was not very precise. The accuracy of the camera was not so good. So we have now higher accuracy, this one, which is giving better guiding stars. And this is the motion control of the instrument itself. It uses the National Instruments Compact Rio 9032 for command and control. And this is the motors drivers. We have much of motors inside this instrument, so we have many drivers for these motors. And this is a control interface for the KFISP itself. Is now you can control everything, either to have calibration module or to observing or to calibrate when you are using the flat fielding, or to make spectroscopy. And if you want to make observe, you can also only press this button. And this is the filter wheels and the Grismy wheels. You can choose which one. Also, and this is the polarimetry portion of the interface. This is the camera interface, camera control interface also. And it is both interfaces are on the same computer, so the observer is staying on the same computer and can observe and can move can choose which instrument to use, and also we can make this sequence for observation, and he can, if you want to leave the place and do everything, he can do. This is a pinhole image that I talked to you now. Has some holes for focusing of the instrument through the collimator that I talked to you about now. And this is one sample of the direct imaging of M67 star cluster. This is spectroscopic calibration also. And this is one of the polarimetric imaging we have. Actually, we don't have much experience related to polarimetry, and this is one of the might be the we have to collaborate with you in this polarimetric observation. For more information, we had three papers published for this instrument. You can refer to them. This one in experimental astronomy, and we can refer to it if you need more information about this instrument. Also, we have another smaller telescope, which is 14-inch telescope inside this small dome, and it has an SC big camera. Also, we have 11-inch near-Earth object telescope, which used for tracking of the satellite tracking and near-Earth objects. And this is the last one, which has this Kepler CMOS KI camera. It's very expensive camera that just arrived before I come to here. We will use it for near-Earth object observations. We have also some miscellaneous instruments that this is the luminosity lens that I talked to you that have upgraded now and it's working now with Siemens control system. And we have an all sky camera and we have also weather station. It is known to you. So we have now some projects that are working projects that for observing and studying astronomical transient phenomena with our 1.9 telescope. So we can now we have a lot of observation related to supernova, gamma ray burst, the AGN, and binary stars, and gravity waves, and other variable stars, and also we have discovered another project, running a project now to study near-Earth objects using Kottamia Observatory telescope, which are these 3 telescopes to observe asteroids, comets, and artificial objects that include man-made satellites and space debris. We have some collaboration with some international groups that these are the groups we are collaborating with them now, the WEBT now. We have collaboration with this Whole Earth Blazar telescope. Also, we have collaboration with the Grandma network, and also we have some collaboration with some Spanish group, and we have also some collaboration with French and Spanish groups to study stellar occultation, minor planets, and we have also collaboration with Black Hole Tom, and collaboration also with an Indian and Japanese research group in particular supernova study. This is also collaboration with international groups related to near-Earth objects. We have international scientific optical network collaboration with them, ISON, which is the Russian Academy of Science. And I think we have one node here in Cape Town also. We have also a Minor Planet Center collaboration, which we are collaborating with them now, and which we actually we have a lot of work with them last 3 years. See now. As you can see now, this is the discoveries we made with this network, Minor Planet network, using our 1.9 telescope. These all are for our 1.9 telescope, which is 088 node at that site. So, why you are looking for another site now? This telescope is working very well now, and we have a very advanced instrument, and the telescope is working very well. But the problem is that the government started working to build another an administration capital very near to this Kottamia Observatory. That we can see now, these buildings are very near to our observatory now, and we can see the light pollution will affect us a lot, especially the coming 5 years. We hope they will be very slow in doing such light pollution, and we started actually looking for another place to build a new observatory in order to fill the gap between Asia and America, and between Europe and South Africa. You can see here there is any observatories or telescopes other than the Egyptian and South African telescopes. And we are also a regional telescope for the MENA region. So we started looking for candidate locations for this future telescope, and we found many places that can be probable candidate for the future telescope. We found many locations here in the west of Red Sea, and also we found some locations in the Sinai Peninsula. Sinai Peninsula actually is the borders of Egypt, and it has here Israel. in the borders of the north borders. So these are where the seven locations we found at the Red Sea region, and we found that there are 3 locations in Sinai Peninsula region, and this actually were the best, because the other location in the Red Sea will face the problem of light pollution after some years. Because of the urban extension and the touristic projects that the government is making at that place. So we decided to start working in this location at Sinai Peninsula here, in this location actually, which is called the Rujom Mountain, and we had field trips to these candidate sites with our colleagues, as you can see here. So we finally get the action to make our future telescope at this location at Sinai Observatory, which was made by our previous director. We made this foundation stone about in January of last year, about 1 year ago. And we started moving the site testing equipment to there, as you can see here now. We started moved the site testing equipment, and we already installed most of these site testing instruments. It was supposed that we were going to finish this equipment installation in the last September, but due to the war between Israel and Gaza, we had now security problems that we cannot go there until getting some security permits to access these locations. We hope we can have these permits in the near future, and we can continue our work in installation of the instruments, and we can go ahead in the site testing campaign in order to test for this location and to continue for our future telescope, which is supposed to be 6.5 meter telescope. We hope we can get the fund from the government to build this telescope, which I think will need a lot of money. Especially we have now very difficult economic situation in Egypt, like other countries also. But we hope the government promised us that if you found the good place for that telescope, we will give you the fund. We hope so. So this is some images of the location of this Sinai Peninsula telescope, the Rujom telescope, and the seeing was promising at that for one night only to 0.7 seeing at that location. So I think that we have some probable collaboration between our NARIAG Institute and your observatory to have any sort of astronomical observations using our telescope and your telescopes, especially for polarimetry, which we don't have much experience with it, but we have a very good instrument, very good polarimetric observation instruments that we can use if you are willing to make this sort of astronomical observation. And also we can have a collaboration related to near-Earth object space, near-Earth objects, near-Earth space objects, using our Kottamia or your SAAO telescopes. Finally, we can have some stuff exchange actually related to optical, electronic and electromechanical engineering, which is very important actually to us because we have a very shortage number of people that working in these fields. We don't have a mechanical engineer, we don't have an optical engineer only, we have some few electrical engineers. So we need your help in this part of this engineering fields. We hope we can have some stuff exchange between our institute and your institute. And also we can also have some collaboration related to the site testing. So finally, I want to tell you that one of my colleagues has nominated me for the executive committee membership. So please don't forget to give me your vote when there is voting for this in the coming March, inshallah. Thank you very much for giving me the chance to be here and for giving me the chance to be in front of you. And I'm sorry, I'm not fluent in English so much, so sorry for that. We have about 65 astronomers.
At the observatory and some universities?
No, only in the development. In the universities, we have 3 universities that are having astronomy departments: Cairo University, One University, and Al-Azhar University. I am talking about only our institutes of development.
That's quite good.
But we have a shortage of engineering personnel, actually. A very shortage of engineering. So we need to have some collaboration with you regarding these fields, actually.
I was just wondering how do you deal with it? Looks like you have very dusty sites. I mean, the building outside it's quite dusty. But inside, the pictures you showed, it looks very clean inside. So
No, there is no dust. No.
So what is this sort of brownish stuff on the building?
Yeah, but we don't have a very big problem related to dust, actually. We have dust, all the labs have dust, but it is not so huge that you can make it. Only around 1 week in the year that we can have a lot of winds. So it is not so big problem. And the site now is about 500 meters above sea level.
Yeah, I mean, as you know, I visited 2 years ago and I was incredibly impressed by your, the FISP instrument, right? I wish we had something like that on our 74-inch actually, because I think that's something we really need. But at the time of my visit, as you know, we've been talking about the potential to add Kottamia to the network of telescopes in Africa through the African Integrated Observation System. And at the time, you mentioned the fact that there was no internet connectivity to the observatory, but you are hoping in the future that that would materialize. So has there been any advances on getting internet connectivity there yet?
But we have only a cell phone network. We can use it for the internet. It is the okay. But the main problem is that some persons that must be there because of the local generators, because of the current liquid nitrogen, because of the operating of the telescope itself. So there must be some people. So if you need any observation, we can go for it. No problem.
Yeah.
Want you to tell us which observation you need and give us the information about the time and the invitation. You can go for it. No problem. If you have some mutual collaboration, we can do it for anyone. Like we have now with some Japanese colleagues from Japan, they sent us the applications of the supernova or any other objects they wanted to observe, and we observe the same and the same claims the observation later on when we finish. So it is not a problem, big problem to have to join your network. But we can have usual observation bookshop also if we want to do.
As far as the software for that, if you wanted to really move to, say, robotic usage, or even just remote observing with it, I imagine there's quite a lot of development that would be needed. I'm guessing that GUI you showed for the control of the instrument is something that the observer clicks buttons to configure the instrument, but what would be ideal is having that information for an observation in a database that could automatically calculate those Do you think that's something that?
Need some work to software to be done.
Yes, yeah.
The abstract for the colloquium, you mentioned 6.5 meter, but it's not so much listed. Can you tell a little bit about the design?
No, we don't have the design yet. It's not five. But it partially depends on the site testing outcomes. Because we, for example, we will not do a 6.5 meter telescope, infrared telescope, if the location will not be suitable for that. So we have to have site testing results in order to have the design for the telescope. And this is also one of the collaborations that we can get to experience in. Because we don't have don't know about science goals of our telescope, what we can do with this telescope. This will be a big telescope, and so we have to have some science goals with the telescope. Now people are observing only this near-Earth objects or supernovas or and so on. But the future, what's the future? What about the future? What we need in the future? What's the sort of in other countries that we have to have our future telescope?
Where does the 6.5 meter number come from? Based on you want to copy another telescope design?
Actually we thought initially to make it like Tokyo Institute telescope, but later on people said no, we must have our own telescope to start from the beginning. And we have now a design from Italy also. He will show us some design for the telescope, but we didn't agree on until now.
As you know, Egypt joined the BRICS family last year, so I think there's a lot of potential within what's called the BRICS Astronomy Working Group for Egypt to work together with some other interested parties in BRICS, which could leverage, support for development of the ELOT and, going through the whole process of design trade-offs of, whether you go to this design or that design.
It will be fun. It will be fun to do this.
Okay, there will be no more questions. Let's thank Yosry again.
Thank you.